In this video, we'll be discussing the fifth section of Chapter 2, motion with constant acceleration. So what does that mean to have constant acceleration? Well, if we take a velocity graph here shown, if it is constantly changing, in other words, if the slope of the velocity graph is a straight line, if it's a constant slope, then we have constant acceleration. Remember we said before that the acceleration is the how much the velocity changes with time. In this case, we have a change of 27 meters per second in a time interval of 1.5 seconds, which gives us an acceleration of 18 meters per second squared. So we can use the definition of acceleration, delta v over delta t, to define our first kinematic equation. To do this, oops, let's use the pen. Right, I'm going to take this expression as it's written here, and I'm going to multiply both sides by delta t times delta t. I'm going to ignore this thing in the middle. And on the right-hand side, the delta t's cancel, and here I have a sub x delta t is equal to v sub x final minus v sub x initial. Now I'm going to solve for v sub x, so I'm just going to add v sub x initial on both sides. That's v sub x. And so over here, these cancel, and I'm left with just v sub x final. Sorry, that's what I'm solving for. And that's equal to, on the left-hand side here, we have v sub x initial plus the acceleration in the x direction times my time interval. And you can see that is exactly what's written here in the book. This is an expression for how we can find the final velocity given the initial velocity, the acceleration, and some time interval. That's our first kinematic equation. Okay, so we can derive more constant acceleration equations by looking at the graph of the velocity versus time graph. So let's say I consider this time interval from t initial to t final when my object goes from some random initial velocity to some random final velocity. Now we said before that the displacement is the area under this graph. Now in this case, the shape that's created by this graph is a triangle plus a rectangle. So what I'm going to do is I'm going to find the area of the triangle, and I'm going to add it to the area of the rectangle, and that will give me the total displacement. Okay, so let's do that. Okay, so the area of the triangle is equal to, well, we know a triangle is 1/2 base times height, right? Times height. So in this case, the base is t final minus t initial, or delta t. And the height is this v final minus v initial, or since we saw just on the slide before that v final minus v initial is equal to a delta x, I can write that a sub x, I'm sorry, a delta t, excuse me. Good. So let's simplify this. I have a 1/2 a sub x. I have delta x times delta x. That's simply delta x. I'm sorry, I keep saying delta x. I mean to say delta t. Delta t times delta t is delta t squared. At least I'm writing the right thing. Okay, so that's the area of the triangle. The area of the, right, so that's this one here. The area of the rectangle down at the bottom, this one right there, is equal to, well, this is just base times height. So here I have the base is delta t, and the height is simply v initial minus 0. So it's just v sub x initial. Okay, so I can sum these up, and we know that the area of the triangle plus the rectangle is equal to the displacement, delta x, because our displacement is equal to the area under a velocity graph. We know that. And that's equal to, what do we have here? let's write this one first, the rectangle first. So it's v sub x initial delta t. I just rearranged things a little bit, nothing big, plus 1/2 a sub x delta t squared. Sub x delta t squared. Good. Now the last thing I'm going to do is I'm going to, instead of writing delta x here, I'm going to write this as x final minus x initial. So I'm going to go to a new page to do that. So the left-hand side, x final minus x initial is equal to, and I'll go back, you guys can also rewind, the right-hand side, vx initial delta t, vx initial delta t plus 1/2 acceleration in the x direction times delta t squared. Solve for x final. X final is equal to, so which basically means I'm going to add x initial to both sides. So this is equal to x initial plus vx initial delta t plus 1/2 a sub x delta t squared. This is my second very important kinematics equation. You can see it's written here, much neater than mine, so it's okay if you didn't miss it. Right, here's another kinematics equation. So now I can find the final position if I know how fast I'm going at the beginning, what my acceleration is, and how long my motion is changing. Okay, so let's review. So we saw both equation 211 is given in the book here, and we derived equation 212 here, just the ones that you saw just before. We can combine these two to get a new relationship, another equation that's very useful. So to do that, I'm going to take 211, I'm going to start with this one right here, and I'm going to solve for delta t. So solve this for delta t, so I move vx initial to the other side. So I get a vx final minus vx initial is equal to a sub x delta t. All right, so that's just moving the initial velocity over. And then I can divide both sides by the acceleration. So acceleration cancels on the right-hand side, and I see that delta t is equal to v sub x final minus v sub x initial over a sub x. Okay, now I'm going to take that and I'm going to plug this into equation 212. Okay, so 212, I have x final is equal to x initial plus v sub x initial delta t plus 1/2 a sub x delta t squared. Okay, so I'm going to need a little bit more room to do this, so I'm going to do this on the next page. So let's start again. X final is equal to x initial plus vx initial. Now my delta t, I'm going to plug in what I had before. That's vx initial minus vx. Final minus initial. Final minus initial over the acceleration plus 1/2 times the acceleration times delta t squared. So it's just this thing again, but squared. Vx final minus Vx initial. Now this whole thing in the numerator is squared over a sub x, which is also squared. Okay, it's getting a little messy here. So I'm going to move my x initial over to the other side. So it cancels over here. I have an x final minus x initial. And what else am I going to do? I'm going to distribute this initial velocity here. So I have a vx final times vx initial. And you know what, I'm just going to drop the subscript x on all of the velocities because I know that I'm in the x direction right now and I can put them back in at the end. So I have v final times v initial minus v initial times v initial. That's v initial squared. All of that is over the acceleration. Plus, now here, this acceleration cancels with one of these on the bottom. So I have a 1/2, right? So that 2 goes to the denominator. So I'm just going to put a 2a sub x down here. And on the top, I'm going to square this whole thing. So I'm going to FOIL this out. The first is v final squared. V final squared. The last is v initial squared, right? Minus something times itself. Minus minus is a plus. So I have a plus v initial squared. And then I have the two cross terms, minus 2 v final times v initial. Okay. Let's multiply everything by a sub x. Actually, let's multiply everything by 2a sub x so that this denominator goes away. So the left-hand side becomes 2a x final minus x initial. And then I need a 2 times all of this. The acceleration will cancel. So I have 2 v final v initial minus 2 v initial squared. Plus, now the right hand, this term, the second term, the denominator goes away basically, and we just have the numerator left. V final squared plus v initial squared minus 2v final v initial. Good. Well, this is the same as that, except this is positive and the second is negative, so they cancel. I have now 1 on the right-hand side here. I have a v final squared, so I'm going to write that first. And I have negative 2v initial squared plus a v initial squared, leaves me with 1 v initial squared. And the left-hand side doesn't change. 2a, adding back in my subscripts, x final minus x initial. And yeah, this is actually the more or less the final way that we write this. We can also write this 2a sub x delta x, if you prefer, is equal to v final, v sub x, let's put our subscripts back in, final squared minus v sub x initial squared. So here's another very useful kinematics equation. This one's particularly useful when you don't know anything about how long, the amount of time that something is moving, because time doesn't show up in this equation, so it can be very useful. Here our book writes it, this is equation 213, a little bit slightly different form. Note that this delta x here, as it says, is the displacement, not the distance traveled. Good. Okay, so to summarize, we have 3 kinematics equations that we will primarily use. One does not include the displacement. The second one does not include final velocity. Oops, so no v final. And the third one does not include time. So depending on what information the problem gives you, you can pick out the best equation to use that helps you solve the problem the most efficiently. So you can usually use 2 equations to get to the right answer, but you can also do the same thing using only one of them. It just takes practice to know the best way to find a solution, but getting the right answer is also very good. Okay. Let's do some examples in the next video. I'm going to do this one in 2 parts because it's getting a little too long. So I'm going to come back and I'm going to start with this example and maybe do a couple more examples. Okay.